Jay, we cannot hear you at all.
I unmuted.
Yeah, you were.
It
Thanks.
worked. It worked. Okay. Sometimes I don't know if this problem with the Zoom or problem with what.
Yeah.
Ladies, are you able to hear me now?
Yeah. Not
Okay.
as good. Thanks.
Okay. So if you go to here, content. So I have the assignment. This is for the assignment student. So I have the assignment here. So which is the seventh assignment. I have asked the seventh assignment. Okay. Of course, you cannot see the solution, but a seventh assignment is the assignment which is based on deadlock. So this one is due was yesterday released. So this one is due on coming Monday. So, which is due before the assignment 6. And I think today we'll complete this. Already we completed this before. I just want to emphasize this and this part, these topics also we completed last class. See here, when the down arrows means that this, I mean, here I just want to explain the symbols. This down arrow means the P2, the arrow is pointing to P2, which means that resource has already been acquired by that process. Okay. So if it's the arrow is going to the resource, that means that resource is not yet acquired. It is like asking for that resource. Is this clear? So this should be clear in the assignment. So here, this down arrow resource R2 is already assigned to P2. So P2 is holding the resource, and P1 is asking for resource R2. Is that clear? So the arrow here denotes, why we have arrows in that way. So don't get confused with the arrow. So if the resource is already acquired by the process, then it should be a down arrow. And maybe I used arrow. I think I used consistently in my lecture also to use the down arrow if it's been acquired. And P2 is also requiring for resource R1 now. So whether this process can continue its execution or not, and of course, it's very simple. So if you see this is the resource allocation graph or whatever, and it is a directed graph, right? And this is a directed graph. You should know what is a directed graph from 250 course. But I hope it is clear. So P1 is requesting for R2, but R2 is already held by P2. So that should be clear. So why this arrow, where the arrow is going, it should be clear. So don't get confused with the arrow for the assignment students I'm talking about. So this is due on next Monday. Please do submit the hard copy of the assignment as well as the soft copy of the assignment in D2L. And assignment 5, assignment 6, the only thing I didn't cover, I don't know whether I have the time to cover today, but see, if you can Google about this, of course, I mean, I searched, and this is using the reference bits. So if you can understand this question, it will be well and good if you can do by your own. So this is using reference bit, and your which page is most recently referred. If you can do by your own thing, otherwise if you cannot do, I'll explain this on Monday's class. I'll do as a research component, and I will help you with this assignment question if you cannot figure it out. So that's why this assignment is due on next Wednesday, not on Monday. Okay, this 6, of course, ordering is 6. It should be due earlier than 7, but since because of this topic I didn't cover, I'm asking this assignment. So if you have time, you can complete by yourself. If you don't get the answer to this question, then I will discuss this on Monday's class. Okay, for now I will give as a research component. You do the research. Okay, so and I hope Sarah gets that, right? Are you able to follow? Because you're doing the assignment part, right? And Samantha as well, right? Okay. So now we will talk about the class. And other than that, actually, I need assignment 1 and 3 from you because there is a bit accreditation which is due this semester, not this semester, this coming June or something like that. So assignment 1, I gave the sheet to you, and assignment 3 also. Assignment 2, there is no thing to do, but assignment 4 also I gave to you. Is it that right? 1, 2, and 4 I graded. So can you please hand over the assignment sheet to me, because I will take a photocopy of that and return the assignment to you. Because Dr. Haklin Kim was telling that we need to submit the assignments to the ABET team. ABET is, I don't know, American Board of, I don't know, like ABET is an accreditation for the program. So please do hand over your assignments, hard copy of the assignment to me. I'll take a photocopy of it and give it back to you, because I need to show that assignments to the accreditation team when they come in I know, I think it's due on June or something, but please do return back 1, 3, and 4th assignment back to me. Is that clear? I will give back to you again. So don't worry. I'll take a photocopy and give back the assignment to you. Okay. If
What exactly do you want us to give you?
you want to give me, you give me the graded assignment. If you're not taken the graded assignment from me, it should be with me. But if I return back to you, please give it to me. The graded assignments. Are you clear? Did you pick up the assignment from me? I don't know who was talking. Did you pick up the assignment
Uh,
from me?
it's Victor. No, I didn't pick it up. I submitted it digitally.
Okay, so you submitted it. If you didn't pick it up, then no problem. I have it with me. If I gave the if you have picked the assignments from me, the graded assignments, then please return it back to me. I need to make a photocopy and then I'll return to you back. Okay, is that clear? For 1, 2, and 3, because for 1, 2, and 3, I didn't ask you to submit in Dropbox. Did I ask you to submit in Dropbox? Okay, then it's fine. Okay, if you have already submitted the Dropbox, then it's fine. I think I got confused with the other codes, 141. But anyway, if I graded your assignment, please give it to me because I have already marked, I have taken points, etc. Please return to me because I didn't mark the this thing. You will give it to me, give it back to me because I need to know where I took points, etc. And I need to do that. I don't want to regrade the assignment again by because Dropbox is just for my reference. Is just that to see that you have submitted in case if I lose the assignment. But always submit the assignment hard copy as well as a soft copy to me in the future. And for the few graded assignments, if I handed over the sheet to you, please return back to me. I'll give it back to you again. I will take a photocopy and return back to you. This is for ABET. Okay, so this is for the ABET and it is due. And we know that the computer science program from I'm not security, the computer science from program from East Torsberg is ABET accredited. So which means that you can transfer to the courses because it's recognized by ABET. You can transfer to other universities, etc. They recognize that okay, whatever we are teaching is actually according to their guidelines. Okay. So back at Lockhaven, the computer science program is not accredited by ABET. It has advantages, there's disadvantage. I don't want to talk about ABET accreditation now, but let's start the class. Okay. So let me start the class. I want to complete the topic of deadlock. So we were discussing over the banker's algorithm. The banker's algorithm is actually prediction algorithm, which is predicting the future. And actually what we are trying to predict the future, whether there is going to be a deadlock or not. So this is a deadlock avoidant algorithm. So there are 3 techniques I told. One is deadlock prevention and one is deadlock deadlock avoidance, and one is deadlock detection recovery. So what I am discussing is about deadlock detection. I'll talk about prevention. Prevention and all is very easy. But what we are talking is deadlock detection algorithm. Is that right? So I'll just open the open the whiteboard and start working on that. I'll just write some few points I want to give. I want to write. I don't want to type. I just want to type. Sorry, I don't want to write. I want to type. So deadlock avoidance. I just want this to go away. Okay. Deadlock avoidance using banker's algorithm. So only banker's algorithms is used for deadlock avoidance. Okay. And in that case, we have maximum, which is nothing but maximum number of resources X, Y, Z. I mean, X, Y, Z, in this case, 3 resources, which are necessary to complete completion. That is given already in the question. See, only I will tell you the problem. Allocation is that allocation will tell you that number of resources, like in our case, let's say X, Y, Z, it can be more than that, right? It can be 10 resource, 20 resource, whatever. But X, Y, Z, which are allocated to processes P0, let's me call P0, P1, and P2. So there are 3 processes at this point of time. So at this point of time, this is the current scenario. Is that clear? So this is very important at this point of time. And all this information are given. then we have to do the future. So future tells that in order to avoid deadlock in the future. So this is why I explained the time machine actually to complete the execution. I hope you can understand the analogy with the time machine here. So in the future, I want to avoid a deadlock. Currently, we also check whether it's a safe state or unsafe state. And I told what is safe sequence, unsafe sequence. So see, safe sequence definition is that, what is the definition of a safe sequence? If there exists at least one possible way of execution in which all the resource requirements, resource means here 3 resources in this particular case, resource requirements of all the processes are met. In this case, there are 3 processes again, all the process resource. If there exists at least one possible way of execution in which resource requirements of all the processes are met, then it is called as safe sequence. So unsafe sequence means, what is unsafe sequence? So these are a definition given in the textbook. I'm just writing again here. What is unsafe sequence? Again, there's opposite. If there is no one, I will just copy and paste. I don't know whether it'll unsafe sequence. Control copy. If there is no possible way of execution, in which resource allocation of, it's not, my is hanging, see. If there is no possible way of execution in which resource allocations are, I said, are not met. If there is, I don't know how to say, if there is no possible way of execution in which resource of all the processes are not met, then it's called as unsafe sequence. I hope my English is right. If there is no possible way of execution in which resource requirement all cannot be met or not met. My English is that, so it cannot be met, right? If there is no one possible way of execution in which resource requirements of all the process cannot be met, if there is an error in the sentence, please correct it. But this is what I want to make us say. Then we define what is a safe state. A system is considered to be safe if there is at least one sequence. I think at least should always be having a space. At least one sequence in which we can satisfy one sequence, if there exists at least one sequence in which we can satisfy resource requirements of all processes. That means what it says is that there should be at least one safe sequence. That is called as, the system is to be in the safe state. If this, I just want to scroll. I cannot scroll. Okay. Zoom. Why suddenly nothing is working? Okay, I think now it's working. So, and if what I want to say, if system is unsafe, okay, unsafe state or unsafe system, if the system is unsafe system or unsafe, if the system or see, unsafe system is there is no possible. If they don't, it's opposite of unsafe system, opposite of unsafe state. Basically, if there is no one sequence in which, exactly, if there is no, of course, this is the definition from the textbook. I'm writing my own words. A system is considered to be unsafe if there is no sequence. If there is no sequence in which we can satisfy, if there is no sequence, which means at no safe sequence, no safe sequence. I hope you are understanding the point. So these definitions are given in this different textbook in different ways. I'm trying to synthesize whatever I understand in my own words. Okay. And I'm trying to zoom. Zoom is not working. Sometimes I don't know why this is. Okay. And now I will type again. In case if we can find a safe sequence, deadlock cannot happen. Okay. And if the system is unsafe, if the system, I mean, this actually goes to the previous point. So if the system is unsafe, I'm not telling that deadlock will happen. So that's what I was telling. If the system is unsafe state, there can be deadlock. There can be a possibility of deadlock. There can be a possibility of deadlock. So that means that deadlock is not always happening. There is a possibility that there can be deadlock. So there can be a possibility of deadlock if the system is in the unsafe state. That is all these definitions. Is that clear? So I hope these are the things we want to synthesize from the trying to understand from the banker's algorithm. I'm trying to pinch in, zoom in. My system is so slow. It's not scrolling up and down. It's doing that, but this pinching is not working. See this. This is actually a problem with it's not capturing my. Again, it's see my CPU is heating up and etc. This is again the problem of how this code is being written. It is not detecting my zoom in, pinch in screen. Okay, I think okay now it is doing that. Okay. So this is all what we want to tell. So definition. So let us do one more this thing, and this is very important. That's why I'm going to give one more example. So the current allocation graph is given like this. Current allocation. One more example of the banker's algorithm. So one more example. So current allocation. Ink is too thick. And maximum needed. So see, this is a maximum. This is not total needed. It's the maximum needed. And there are three resources. In the previous case, I said X, Y, Z. Now I'm going to say R0, R1, and R2. And maximum needed is R0, R1, and R2, right? And P0, P0, P1, and P2. P0, P1, and P2. So R0, R1, R2. So see, this is the current allocation. So P0 is holding one instance of R0 and zero instance of R1. See, R0, R1, R2 are three different resources. Okay. Is that clear? Three different resources. One can be printer, one can be scanner, one can be a light pen, or one can be this pen, this whatever I'm using, stylus pen or whatever. So, so these are three different resources. Okay. And so this is 2, and this is currently allocated. So this means that P1, P0 is holding one instance of R0 and 2 instances of R2. And here it's holding, P2 is holding 3 instances of R1 and one instance of R2. And P2 is holding 1 instance of R0, 0 instance of R2, and is 2 instances of this one, right? And the maximum needed for P0 is actually, it needs 4, 1, and 2, and 1, and 5, and 7, and 1, 2, 3. So this is the maximum needed. Somehow we came to know that this is the maximum needed. Like a time machine, I go forward in time and I know that, oh, these are the requirements. These are the requirements for the process. This is the maximum needed. So this is given, and available is basically, available is given as how many resources are currently available, because these resources are held by the processes, and available is basically 220, right? Which is here 220 means R0, R1, and R2. See, if you're going to read William Starling for this study, trying to understand his algorithm is very difficult textbook to read. Actually, if you're going to read, I think Tannenbaum much better, and I think other books are much better in explaining this. Then we have future matrix. So how do you know the future matrix? Future. See, these are the currently allocated. So future matrix also should have R0, R1, R2. And who can tell me the future matrix? How do you get the future matrix? In the future, I need these many resources. So how you calculate the future from the previous class?
The maximum needed. What's the current allocation?
Not the plus. I mean, already this has been allocated. So maximum needed is 4. So how you calculate in the future, how many I need? It's you subtract this matrix with this matrix.
Subtract 3.
Yeah, 4 minus 1 is 3 difference. In the future, I need 3 more, right? Are you able to follow this? Ben and Kane and Joshua, Justin. Yeah. Okay. And 1 minus 0 is nothing but I need 1. Yeah. And 2 minus 2 is basically 2 is already allocated. So in the future, I don't need anything for this R from R2 for process P0. And Nadisa, can you tell me what is the next one? 1 minus. Nadisa, are you there? Stephen? No one is
Yes.
responding. Okay, can you tell me what will be the P1? 1 minus 0, is that right?
0, yeah.
Yeah, 1. And 5 minus 3 is what? 2. And 7 minus 1 is 6. And 1 minus 1 is 0. And 2 minus 0 is 2. And 3 minus 2 is 1. So sometimes they call future matrix, but in the book, sometimes they give need matrix. So need matrix. So this is the future need, right? So need matrix or future need or whatever, this is called need matrix. So you know how to calculate the future matrix, right? So you are given this in the question is given current allocation is given, and it is given the maximum needed is given, and the future is given, right? So see what the banker's algorithm is that it is going to execute different sequences, different possibles. How many processes are there? 3 processes are there. So there are three factorial ways of doing. If you know about discrete math, if you know about combinatorics and probability, there are how many sequences you can make from this is you can make 3 factor because there are 3 processes. There will be 3 factorial ways. So banker's algorithm is going to try 1 sequence and see that if that system, if it can find at least 1 safe sequence. See, there can be more than 1 safe sequence. Is that right? But if you can at least find 1 safe sequence, then the system is going to be in the safe state. Is that right? So it is going to see what order of execution that I should follow so that in the future, I don't have a deadlock. Is that right? In the future, I don't have a deadlock. So this is the current state of the system. Current allocation is the current state of the system. So in the future, I'm going to see whether I'm going to have a deadlock or not by trying all the possible sequence. See, now availability is 2, 2, 0. Can you meet the resource allocation of P0 now? Because P0 is requiring 3, 1, and 0 in the future. And see, you are trying to allocate all the resources at one time. That is actually, it is not the case in reality, but we'll talk about the drawbacks later. But it's saying that, see, I have availability is 2, 2, 0, right? So if P0, if we execute P0, can we meet the resource requirement for P0 now? Is it possible? No, right? So P0 cannot be done. How about P1? So P1 is requiring 1 and 2 and 6. Is it possible to meet the resource requirements? Actually, it's not is 6, actually 0. Is that right? Oh, it's a 6 actually. Okay. I think in my example, I'm sorry, I will make this as changes because I want to follow the example that this is not 6 actually, this is 1. You can make this as 1 and 1 minus 1 is nothing but 0. So this will be 0. I just want to follow the example that I wrote. So this is nothing but 0. So can I meet the resource requirement of P1 now? Is it possible? It requires. Yes, right. So P1, I can meet the resource requirement. So P1, I can meet the resource requirement. So P1 is tried first. And Once P1 completes, how many resources it's going to release? So P1 is already holding 0, 3, and 1, right? So 0, 3, and 1. So it's going to release all the resource when P1 completes. I'm not telling during the middle. When P1 completes execution, is going to release all the resource that is held by P1. Plus also we are allocating, from the available resources we are allocating. So if it's allocated 1 to 0, of course, we are not going to allocate 1 to 0. The available matrix is going to change. But what I'm telling is at the end of P1 execution, 0, 3, 1 will be released. And whatever the available is basically 2 to 0. So at the end of the completion of this one, if you add this is like nothing but like a vector, if you want to call it a vector, and vector addition we are doing. So 0, 3, 1 is nothing but it's 2 and 5 and 1. So at the end of P1 completion, so we will have 2, 5, 1 as the available resources. Is that clear? At the end, because we are adding the available, currently available with whatever is held by P1. At the end of P1 completion, we will have these many resources available. Is that clear? Okay. So now we have 2, 5, 1 available. Then we will try different sequence. So again, I will go from, if you go from the first hence to the last. Of course, P1 is going out of the RAM because P1 completes. That means that P1 is not there anymore. Because P1 is completed means what? We are removing it from the RAM basically. P1 is not there. So we have to try with P0 and P2. Can we meet the resource requirement of P0 now? What is currently available? Available is changed. So this is the currently available, right? Can we meet the resource requirement of P0? Is it possible? Okay. How much is available right now at the present moment?
No, it's not possible because P0 is 310 and we'll have
So
2, 5, 1.
P0 needs 3, but my currently available is 2. So I cannot meet the resource requirement for P0. So I cannot do P0, right? So what I want to do is, and I want to try with P2 because P1 is already completed, so we don't have to care. So can I meet the resource requirement of P2? Yes.
Yes.
So and P2 is holding how many resource? 1, 0, and 2. Currently is holding resource, and available is basically if it's going to, let's say it's, after P2 completes, I'm writing, okay? So, so 2, 5, 1. So after P2 completes, you have to add. So 1 plus 2 is
3, 5, 3.
3, 5, 3. So after P2 completes, I'm going to have the available is change. Available matrix is going to change, or available, I don't want to call it as a matrix, or available vector is going to be 3, 5, 3. Okay. 3, 5, 3. And so 3, 5, 3. Now can we try the sequence with how much can we try with P0? So we can try, of course, we can meet the resource requirement of P0. So the safe sequences will be P0 will be, of course, we don't have to write how it is going to meet. So again, we don't have to write the available now because P0, we can allocate, we can complete P0. So the sequence of execution will be like this: P1 followed by P2 followed by P0. So this sequence is safe, right? You may find other safe sequence. See, in this particular example, I think there is only one safe sequence, or there is only one particular safe sequence. It depends, is it? Or maybe two safe sequence. With initially 2 to 0. You can also try with, if you go in that order also, you can, I think you can also have other safe sequence. So the banker's algorithm is going to try all possible sequence, and it's going, if it can find at least one safe sequence, that means that it is going to go and execute the process in that order. Is this clear? Okay, any questions on it? See, one of the problem is that whenever a process starts, it doesn't know, it is not like, it is always like this. So see process, let's say process P1 is starting and is executing for 2 nanoseconds. And then at 2 nanosecond, it might request a request. According to this algorithm, we are giving all the resources at this point of time, actually, but it is not always the case. So at any particular point of time, so banker's algorithm assumes that the resources are released at all when the process completes, it's going to release. And when the process starts, it is going to give all the resources. But in reality, process can release the resource at any point of time. Whenever it doesn't need, it's going to release immediately. And also process can request resource at any point of time. Okay. So can request at any point of time, it can request the resource, right? At any point of time, it can say I need this resource. So after only execution will come to know whether I need a resource or not. So at 2 nanosecond, after the sequence, so after the process runs for 2 nanoseconds, then it's going to say that, oh, I need a resource, like that only, right? So the question is like that. Currently the system is in the safe state. Do you agree? This is a safe system because we found one safe sequence. Suddenly, if you say that P0 request, like let's say, suddenly we see that a requirement, and this is the part of the question in your assignment. Suddenly the P0 saying that I need request request 0 unit of R1. Basically, I don't need any R0. I don't need anything from R0, but I need 1 unit of R1. Suddenly it asks, okay, because 0 units of R2. Whether this request can be granted or not, that is my question. So suddenly the system is in the safe state. So okay, I think system is in the safe state, right? So let me redraw this. Current allocation is looking like this. Okay, current allocation. I will rewrite again. So because I don't want to go back and forth. R0, R1, R2. This was my current state, and this state we found this is a safe sequence. Is that right? This sequence of execution is safe. Because not this sequence, this system is safe because we found that there's one safe sequence, right? I told you that is one segment, one possible way of execution in which all the resource requirement for all the process will be are met. That means that is a safe sequence. That means if we can find one safe sequence, that means the system in the safe state. And of course, the system is in the safe state. I told that we found one safe sequence in which the system is in safe state. So this is a safe system. So you got, because I showed you just a moment ago, this is a safe sequence, right? And in the future, we already calculated the future matrix to be like this. So R0, R1, and R2. So you have to calculate the need matrix or future matrix. It's also called as a need matrix, as I told you before. It's also called as a need matrix. So the need matrix was 3 and what was the need matrix? So how much you come? 310, right? 310. We know how to compute the need matrix. Basically, maximum, this is a maximum. Maximum minus the current is going to give me the need matrix 1 to 0 and 0 to 1. I'm rewriting. So now the request is coming. So P0 is asking for 0 unit of R0 and 1 unit of R1 and 0 unit of R2. So this is R0, R1, R2. So now what is available matrix? Available matrix or a vector is nothing but 2, 2, and 0. Okay, P0 is suddenly asking, see, I need 1 unit of R1. It's making request. So the system is currently in the safe state. I proved that. How it's a safe state? I found a safe sequence, P1 followed by P2 and followed by P0. So the system is the safe state, right? P1 followed by P2 followed by P0 is in the safe state. But what happens is that suddenly P0 is asking for, this amount of resources. Okay, so can I grant this request or not? See how much we are available. R1 we have 2, right? Currently available. This is R0. This is R0, R1, and R2. Is that correct? R0, R1, R2. So it is requesting for R1. Of course, we have one available. So we can take this out and make this 1, right? Make this as 1. And then, of course, when you make that as 1 and we got P0, we are going to give this R1. So this is 1. Of course, then then the need matrix also will change because 1 minus 1 will become 0 here. So this will become 0. So there are 3 changes we have to make. So when I'm going to assign this, request is coming from P0, it's suddenly asking for 0, 1, 0. Then I have to make 3 changes. One is the current allocation, and one is the future matrix will change, and availability vector also will change. Is that clear? So this is going to change. But whether giving this request will make this system safe or unsafe, we have to try now. Is it clear? Whether granting this request. So now everything has changed. Now we'll try again. So before it was in the safe sequence. Now everything changed. Now we will see the available. Now currently available is what? 2, 1, 0, because we granted this is R0, R1, and R2. So we granted, let's say we granted the request, and now we'll see whether the system is in the safe state or not. Again, you're going to follow the same algorithm. So 2, 1, 0, of course, P0 cannot be met the request. P0, we cannot meet the request for P0 because it needs 3 units of R0. How about P1? Can we try P1? P1 is needing 1, 2, 1, 0. Definitely P1 cannot be satisfied because P1 needs 2 units of R0. Is that right? So P1 also it cannot be done. How about P2? P2 is requesting 0 and 2 units of R1 and 1 units of R2. So P3 request cannot be, sorry, P2 request cannot be also granted. That means what we are trying to see is that if you are going to accommodate the request, whether that request should be granted or not, we are trying. But if we accommodate the request, it is moving the system which is safe to an unsafe state. Is that clear? So that means that we will not grant the request. Is this clear? I change everything just to make sure that, okay, if I grant this request, whether this is moving my system to an unsafe state. Of course, it is moving my system into unsafe state. That means that I cannot grant this request. Is this clear? Any question? A lot of people get confused with Banker's algorithm, to be honest. A lot of people get confused. I want to be very clear in this. Anyone, Chara and Samantha, has any questions about this? Who are doing the assignment part has any questions on this? Now, of course, students who are doing the project part also should know this because in the final exam, I'm going to ask these questions to you, right? And how about the Zoom students? A lot of students join Zoom. Any questions on it? See, we're trying, see, the system is in the safe state. The question is that we mean system in the safe state, but we are to say, if we grant this request, whether it is going to make the system unsafe or not, right? I don't know any analogy I'm not getting on the top of my mind. So if I accommodate that request, whether I should grant this request or not, it's basically telling, for example, I don't know, this is like stupid analogy. For example, some student want to waive off the pre-requestee, right, for computer graphics course. So this is my decision, whether to grant the request or not. If I grant the request, they should be they should get a good grade and pass the course, computer graphics. And I have to make maybe I conduct a test for the student and then say, okay, they don't have linear algebra before. So I grant the request. I will say, okay, you come to my class, come to my office. Let me ask few questions. What is the difference between scalar and vector? And let me ask what is cross product, dot product, etc. If you're able to answer the question, okay, I grant the request saying that, okay, thinking that you will pass the course, right? Otherwise, I said I will not waive off the pre-requestee. Is that clear? So I'm just trying to predict in the future. Of course, even if I grant the request, in the future, there must be, some type of, here it is actually in this algorithm, it is predicting the future. See, this is a deadlock avoidance algorithm. This is a good algorithm to avoid deadlock for sure. If you are going to, because it's going to see another thing I just want to say is that even if the system is in unsafe state, it can still be deadlock free. Why? I can give, even like, let us say that this analogy I will give. I think I have this thing. See, it is not always that when there is an unsafe state doesn't mean that it is going to be deadlocked. Okay. Why? Let me give another example. See, for one thing for sure, if the system is in safe state, it is deadlock free. The Banker's algorithm will guarantee that. If the system is unsafe system, there is no one possible sequence which will be, which can guarantee that the resource requirement for all the processes are met, then it may lead to deadlock. It may lead to deadlock. I'm not saying that it may lead to deadlock. I am not telling that it can lead to deadlock or it will be leading to deadlock. Okay. This is the right word, I think. It may lead to deadlock. So let's give me another example. So process. So there are two process P0 and P1. Currently allocated is currently it's holding two of this one, and this one is holding one. And the maximum is requested by this process is 5. And for this process also 5. Of course, in the future, how many you need? Basically, you subtract this. 5 minus 2 is 1. And 5 not 1. 5 minus 2 is 3. And 5 minus 1 is 4. In the future, I need 4. So the currently available, let's say the system has 5 printers. I mean, let us give me 5 printers. And available is basically is 5 printers. Of course, how much is already taken? 2 is taken by P0 and one printer is taken by P1. So the available remaining is how much? 5 printers. How much is the remaining printer I have? Available, currently available. Who can tell this? I have 5 printers. So P0 is holding 2 printers and P1 is holding 1 printer. So how much is available? 2 printers. Yeah. 2 printers are available. Is that right? Any questions on it? System has 5 printers. Already P0. So current means what? I mean, I don't know what I used before. Yeah, current allocation. If you want, you say current allocation. No, I skipped because currently current allocation. Okay, I mean allocation I wrote on the top. So current allocation. So currently P0 is holding 2 printers and P1 is holding 1 printer, right? And can I see this system is unsafe or safe? Because in the future it needs 3 printers. In the future, this needs 4 printers. So this system is safe state or unsafe state? Safe? How? Unsafe. Yes, the system is in unsafe state, right? So it is unsafe because in the future I need 3. In the future I need for P1 is 4. Is that right? But it is an unsafe state. But still I can say this can be deadlock free. Suppose, let us say P0, we don't know how P0 is going to complete, right? Suppose P0 is holding, I mean, in my case, P0 maximum. In the future, it's need 3 printers. Okay. So I don't know why I just didn't. I don't know. I forgot the sheet, anyways. So suppose it can so happen that P0 is holding 2 printers. Maybe it is happening that P0 is executed and it is releasing the 2 printers that it has. It completes its execution. It is releasing 2 printers. Okay, because you should remember that a resource can be released by a process at any point of time. It is not always at the end of execution. During middle also it can release the printers. After it's done with printing, why it needs to hold the printer, right? So it can release 2 printers. So now available will become 2 plus 2 is 4. 4 printers. Of course, it released this one, and it may need in the future, maybe it still needs 3 printers, but now 4 printers are there, right? So then P1 can execute, and P1 needs future 4 printers. So P1 can be given. Now P1 has, we can give all the 4 printers to P1. It can happen. This order of sequence of execution is possible. So P1 can hold all the 5 printers. And then when P1 completes, it can release this thing, and the future P0. It can be different. Okay. I'm telling you in a counter example in which I says that a system which is unsafe state can also be deadlock free, because it depends upon how the requests are arriving and when the process is releasing the resource and when the process is demanding that resource. Is that clear? So it is, I'm telling that this system, a safe system doesn't mean the unsafe system doesn't mean that it is going to be leading to a deadlock. Is that clear? Any questions? Is that so? Unsafe system can lead to may lead to deadlock, not can, may lead to deadlock. Okay, or can also, right? I don't know. But may lead to deadlock. I'm not saying unsafe system will lead to deadlock. Will means it's a must, right? It is not will lead to deadlock. It may lead to deadlock. Unsafe system. Is this clear? So one of the problem with this approach is that, what is the problem with this approach? This is a well good algorithm. Of course, this we can get current allocation. You can examine the system and get The problem is that how you know that this many resources are I need in the future, right? That's a problem. Yeah, how do I know that 4, 1 and 2 is needed? Because process, like it executes some line of code, then it requests for some device access, etc. And then it executes some line of code, then you'll ask. We cannot say that it requests, we cannot say for sure, until you examine the code, etc. And until it's a finite number of process, unless it's a real-time system where it's a finite number of process, well-defined process, we cannot say for sure that this many I require at the maximum at the beginning. We cannot predict the future. So that is the main drawback of this algorithm. We cannot know the maximum amount that in the future this is required or not. Is this clear? So maximum amount is basically we cannot know this value this is hard to predict. That is the main drawback of this algorithm. Is this clear? So this Banker's algorithm is actually a deadlock avoidance algorithm. Banker's algorithm is a deadlock avoidance algorithm. Any questions here, students? There's one question. So definitely I'm going to say 100% there's going to be one question on this in the final exam. Okay. So you should understand Banker's algorithm correctly. And all the subtraction, everything, make sure that you do, because I'm not giving a finite time for you to complete. I mean, of course, I'm giving a finite time, but that finite time is large, not 3 hours. It's the entire day to complete the exam. Is that clear? So please do all the subtraction. Don't make any mistakes. Okay. See, one thing is for sure, if the system is safe, it's going to be deadlock free. That Banker's algorithm will guarantee. The system is safe, I'm telling you. Banker's algorithm doesn't guarantee that it's going to be deadlock free. If the Banker's algorithm can find one possible way of execution in which there is a safe sequence, then the system is going to be deadlock free. So the Banker's algorithm is going to try every possible sequences. Is that clear? Any questions? See, one thing I just want to see, or be like I explained this in the last class also. See, when batch processing is all non-preemptive scheduling algorithms, shortest job, shortest remaining time, shortest job, first come, first serve. There's no problem, there is no preemption, nothing happens. So there is no problem of mutual exclusion, or there's no problem of deadlock, because one process completely, but the problem is that it's going to be uniprogramming. So those days I was not born, but those days it was punch card system people are using, including my PhD supervisor, master supervisor, or including Professor Hacklin came, or Professor Hofmeister. They might use punch cards where they punch, I don't know how it works. They go to that operator and give it, and one process cannot run one time. So what is that?
I just think it's funny. Like, I mean, they still use the COBOL, which still has the space for the punch cards, right? Like, it's still adds over. Like,
yeah, I never seen punch cards in my life, so
I've seen cool.
Okay, but that is not a problem. See, the problem happens when you are going for preemptive algorithms. Why you are going for preemptive algorithms? Because you want to accommodate more number of processes in the RAM, so that we are feeling that all these processes are running. They are running concurrently. Concurrently is different from saying that at the same time. Okay, at same instance of time, they are not at the same nanosecond or picosecond. They are not running. They are running concurrently because we are dealing with single processor. So all these processes in the RAM are running concurrently. So that is the very important. So do you understand why it is say concurrently? It is not at the same time, same instance of time. It is concurrent. Because as a user, we are very slow, computer is very fast. So that is going to be, we feel that the CPU is available to always to us, but actually CPU is in the background is doing a lot of other things, system processes, and doing that, checking everything is fine, and etc. Is that clear? So concurrently, we are running many processes. That is the multi-programming environment. But due to the concurrently running many processes, if there is a shared, because two processes can share the memory location, so then there is a problem. I told that problem is critical section. So we'll talk about critical section in detail, but that can lead to inconsistent data, and also that can lead to a situation like deadlock. Okay, that can lead to deadlock. See, if the process is not run, if suppose, see, the main problem occurs because of preemptive scheduling algorithms. And if all the processes CPU bound, this problem won't arise in even like, the problem arises when two processes are sharing the same resource, right? Otherwise, the problem with deadlock or mutual exclusion will not happen, right? Why we two processes want to share the same resource? One example, I told the counter example, right? When you enter the superstore, you increment the counter value by 1. When someone exits the superstore, you decrement the counter value by 1. You have a question? Will. Okay. Okay. Anyone has any questions? So when there is a shared memory concept, of course, there will be problem with mutual exclusion. There will be problem with inconsistent data, because two processes will be entering into the critical section at the same time, because we don't know how the preemptive scheduling algorithm is going to schedule these processes, right? We cannot find, definitely we cannot say at what point of time this will go, this will go, this will go, because we are going to. So there is two problems. One, because we are using preemptive algorithms, and one because these processes are requesting for resources, shared resources. If all processes are running independently without sharing any resources, then there is no mutual exclusion, there is no deadlock, nothing. Everyone is going to do its, if it's all going to be CPU bound and independent processes. Is that clear? So one process is what we are trying to address one problem, it's going to lead to another problem, another problem, another problem. So we are trying to solve that problem, right? That's why there's no one good solution for anything. That you will see that in mutual exclusion algorithm, when you go for process synchronization, of course, it may look like something is working, but something is actually not actually really working. So I told this is one deadlock avoidance. So then what is the other way of detecting? See, I think deadlock prevention is basically, just want to expand the topic of deadlock prevention. See, this is very easy point to note. So there is also deadlock prevention. I said that prevention is better than cure. So why deadlock can happen is because I tell there is no 4 properties. One is mutual exclusion, right? One is mutual exclusion. What is the definition of mutual exclusion? No two processes or no more than 2 processes can enter the critical section at the same instance of time, at the same point in time. I mean, of course, these 2 processes are running concurrently, but I'm telling that if one process enter the critical section, it should say, stop, don't enter the critical section. I'm using the critical section, don't come. Because if you are coming and modifying something, I will get inconsistent data. So process P0 has to inform other process P1 or P2, whatever, whoever is trying to enter the critical section. This is like putting like a hold, it's like only one person can access the room. If there are many persons cannot access, if one person, Will is in the room, he has to inform that Will, say, I am in the room, you cannot come inside the room, right? That is a critical section. Will is in one room and he's telling, okay, I'm going to use the critical section. I'm going to have critical section. I'm going to enter the critical section. You should not go and access the critical section. You have to stop, right? So we'll talk in detail about critical section, but mutual exclusion is a property that is going to lead to deadlock. Because of mutual exclusion only, the deadlock is happening. I explained that in the lecture before. Please do watch that. And mutual exclusion is one property. And what other property was telling? So hold and wait. Hold and wait means I'm holding the resource and waiting for the other resource, right? So in which case, none of these processes can progress further. All processes will be blocked. Hold and wait, right? I said hold and wait is like P0 is holding R1 and P1 is holding R2, and P0 is requesting for R2 to, because P0 suddenly needs R2. And what happens? R2 is basically blocked. Sorry, P0 is basically blocked because it's asking for R2, which is already held by P1. And of course, the mutual exclusion property says that I cannot give you R2 because I'm holding R2. I cannot give you, I cannot share, right? If the mutual exclusion property, is violated, then P0 also can hold R2 at the same point of time. So I don't care. No, you also can work on it. But what is the problem? If you allow this problem, I'm talking about deadlock prevention algorithms. See, we cannot exclude this mutual exclusion. So we cannot say that, okay, I can violate the mutual exclusion property. If you are going to violate the mutual exclusion property, definitely your data is going to be inconsistent. As I said in the counter example, right? I cannot allow, I cannot say if P0 is going to ask for R2, P1 is using R2 already. I cannot say that P0 can access R2. That means it's violating the mutual exclusion property. mean, that will not happen. And if P1 is requesting for R1, then it is become a circular wait, and both P0 and P1 will be blocked, and both P0 and P1 cannot do any process further. Then your system is going to be actually going to hang up. It is going to, like, these two processes, you have seen this state always. System is going to, you say freeze, the system got frozen. Is that clear? When system got frozen, what you do? What you do? What's that?
Turn it back on.
Yeah, reboot, right? It rarely happens when system in this situation happens, the circular wait is happening. The best solution is to reboot the system, right? So this is actually hold and wait. See, this is actually also hold and wait condition. P0 is holding R1, but it's waiting for R2. P1 is holding R2, it's waiting for R1. The circular wait is happening, and you are waiting for other, and you see, it is a game programming. I'm like, or whatever, I'm taking one thing, and what is your name actually? Forgot. Ben is taking. So I am telling you give me, and you are telling you give me, and we both are like saying, you give me, then you give me. So both are never going to give. Then both cannot proceed, right? If two cars are coming and at the intersection and they are like blocked, he is telling you, you go, and he's like, you go, and both are telling you go and you go, and both are not going to, both are so adamant, let's say, both are adamant drivers. They don't want to, take reverse and leave way, You say you go in the reverse, take the car in the reverse, and then I will make a way for me, I will go. Both are adamant, both are like meeting at the junction, and both cannot, and it's a narrow road, let's say, and reverse, maybe you can go a little bit on the side and you can pay way further to go. But here it is not the case. Both are adamant, you go, and we never go, when we'll be at the same place, right? We cannot go any further. So that is the problem with this hold and wait condition. So we cannot relax the hold and wait condition. See, hold and wait condition cannot be relaxed also. If you can relax the hold and wait condition, I think again, I didn't write explicitly what hold and wait will do. It can lead it to its problem, because hold and wait, P1 will be allowed to execute only if it acquires all the resources, and P1 should not acquire R1 if other resources are not available. So hold and wait, if you relax the hold and wait, either voluntarily, this P0 will give, because I can see if the P0 is very kind enough, it's saying that, okay, I cannot proceed with execution, I will leave way for you. Then, deadlock can be avoided. But the problem is that if, and how long P0 can keep doing it? There is another situation that deadlock happens and P0 is holding and leaving way for the process to go. Then process P0 will actually be starved. It won't be ever able to complete. We cannot relax the hold and wait condition also. And I may be giving a convincing answer. Actually, I don't know the convincing answer. Hold and wait condition cannot be also, relaxed. And no preemption of resource. Also, I said no preemption of the resource. And this is also related to the previous point. If we can allow the preemption of the resource, right? See here, P0 is holding R1 and P1 may be holding R2. P1 might say, let's say I completed 30% of my work with R1. So I complete 30% of the work. And then it's P1 is saying that, okay, I need to, P1 is saying that P1's priority is greater than P0, let's say. And if it's a priority-based scheduling algorithm, then I can say that, okay, you are lower priority, I will preempt you. I will preempt you, which means that I can preempt you the resource. I can get hold of this resource. I can say, here I say no preemption of the resource. If we can allow preemption of the resource, then deadlock can be avoided. But again, see, P1 is used this R1, and P1 is coming and taking hold of R1 because it has a higher priority. Then it can lead, again, it is violating the mutual exclusion property. If you can think carefully, it's again violating the mutual exclusion property. It is going to lead to inconsistent data. Is that right? See, let us say that P0 is printing something. Okay, P0 is having access to the printer, is printing something, and P1 is coming out, it's kicking out, and of the data P0 printed, and suddenly P1's data is coming and printed, and you will get the P1's data also being printed with P0, which is not what we wanted. P0 data should not be printed along. P0 is our own document and will be merged. I'm giving an example. So this situation is actually worst in case of when it's actually having the critical section or shared memory, because it can again, because P1, P0 might work with the registers, etc., and it kind of store some values in the registers, and you are kicking out, suddenly P0, and it will have those data, and those data will be accessed by P1 again, right? The shared memory, and definitely you are violating mutual exclusion if you are allowing the preemption. See, resource mean is not always physical resource. I have given the definition initially. Resource doesn't mean that printers, scanners, etc. It can be the critical section shared memory. Remember that. Okay, if it is going to be R1, and that R1 is supposed to be a critical section, let's say, and it will manipulate the values in the register, etc. P0 might have done 30% of the work, and if P1 is coming and is going to read whatever P0 has done to that values in the register, and is going to copy that values into that, I showed you that particular example. Again, please visit the lecture, the introduction to mutual exclusion, and it's going to lead to inconsistent data if you're going to allow preemption of the resource. So in the deadlock prevention strategies, mutual exclusion also not a favorable situation. See, I'm preventing the deadlock from happening. So these are which condition I can relax, I'm trying to see. See, if all these conditions are going to met, then definitely it's going to lead to deadlock. If I can relax only one condition, it will be deadlock free. So I cannot relax this condition also, because it will lead to the problem of what? Inconsistent data. This is indirectly violating the mutual exclusion property. Is that clear? Preemption of the resource. So these two are actually linked to each other, but in the book they're given separate topics, but they are linked to each other. And another thing, what I told was, what was the other condition? Fourth condition for deadlock to happen. Where is my note? Hold on. Circular wait. See, again, this is an example of a circular wait, but circular wait is not necessarily with two process. Okay, it can be with many process. See, the circular wait, this assumption we can relax a little bit, think carefully. See, if we can order all these resources, in increasing order. So let's say P1. So all this, you put the numbering. Okay. So let's say P1 is holding R1 again, and P2 is holding R2. See, the circular wait happens because P1 is requesting for R2 and P2 is requesting for R1. This is a circular wait condition. Is that right? So this down arrow means that this R1 is actually I'm mixing the arrows. See, I think, I don't know how I use in the assignment. I just want to follow. I don't want to confuse with the arrows, because arrows matters a lot. In the assignment, I think I told you like this, when it's holding, I just want to use the same convention that I use in the assignment. So, so R1 is coming, right? So the arrow is like this. So I'll draw like this. So I will use like this. R1 is held by P1 and R2 is held by P2. Now R1 is requesting for P2 is requesting for R1, or if you want, you can put the dotted lines. Okay, in order to avoid confusion, you can put dotted lines. P2 is making a request, I need R1, and P1 is making its request, I need to have R2. And this is again a circular wait, wide circular wait. So if you draw a graph like this, P1 is waiting for P2 and P2 is waiting for P1. Is that right? This is a circular wait. And I said circular wait can be like this also, P1, P2, P3, and then P3 can wait for P1. So it can be any number of processes. But in the simple case, I'm telling P1 and P2. Okay. Circular wait can happen between any number, n number of processes. Okay. So I'm just taking an example here. See, in circular wait, we can do one thing is that I will write this process has, we can modify this algorithm little bit. processor has to acquire resource only in increasing order. That means the resource has to be numbered. So if it is not possible to acquire a resource in the increasing order, then please replace. If it is not possible, if it's not possible to acquire resource in increasing order, okay, you can complete the sentence. Then process must or process must release or will release, whatever you want to call, will release, process will release all the resources that it is holding. Are you able to follow this sentence here that I'm writing? See, this is again, I'm talking about deadlock prevention strategy. So as I said, deadlock prevention strategy, mutual exclusion we cannot violate, hold and wait also we cannot violate, no preemption of resource also we cannot violate. In deadlock prevention strategy, see, these are the necessary, if all these conditions are going to be there, then the deadlock will happen. Even if we can relax one condition, that means that deadlock will not happen. That is a deadlock prevention strategy. As I said that I cannot avoid mutual exclusion, hold and wait, no preemption of resource, but I can relax one condition in which I can avoid deadlock. What is this condition? That is the circular wait condition. Why? See, listen carefully. P1 is holding the resource R1. Okay. P2 is holding the resource R2. And P2 is still executed. So P2 is still scheduled and P1 is requesting for R1. So the resources are numbered in the increasing order. In this case, what happens is that P2 is asking for R1. Okay. P2 is already having R2, but P2 is asking for R1 and P2 is still scheduled. First P1 got scheduled and it acquired R1. Next P2 got scheduled and it acquired R2 and as well as it's asking for R1. But R1 is already held by P1. But what? The resources are numbered here, R1, R2 in increasing order. So this R1 is 1 is less than 2. Is that right? 1 is less than 2. So it can request resource in the increasing order, but it cannot request resource in the decreasing order. So here it acquired R2. It's saying the resource R1. R1 is, I'm telling all the resources numbered here. So if it is numbered here, it cannot request in the decreasing order. So R1 is actually less than R2. 1 is less than 2. Is that right? Then what the algorithm says is that then P2, you release all the resources that are acquired by you. So then P2 will release this resource as well because P1 cannot acquire R1. Why P1 cannot acquire R1? Because R1 is less than R2 because here the resource is numbered. So 1 is less than 2. It cannot request a resource which is decreasing order. It has to request resource in the increasing order only. So what happens is that P2 will, since P2 is requesting for R1, but R1 is the resource which is in the lesser order, right? It is a decreasing order. It can request resource only in the increasing order. Then what it says, the algorithm says that P1 will release R2. Even if it has acquired, let's say P2 acquired R3 also, let's say there is an R3, it is going to release all the resources. It is going to release all the resources. Then what happens if P1 is getting scheduled? Of course, P1 is going to schedule. R2 is already released. So the request for R2 mean P1 will come again. And P1, okay, then it sees, okay, R2 is already released by P2. Then it is going to take control of R2. And then P1 is going to complete. P1 is going to proceed in further execution. And P1, once it's complete, is going to release R1 and R2. In that case, P2 can acquire R1 and R2 or whatever. Is this clear? See, if P1, let's say P1, P2, P3, and there are resources numbered as R1, R2, R3, what I'm saying is that P1 acquires R1. Okay. Let's say P2 is already acquired R2. No, let's and P2 is scheduled, and P2 will see, okay, it will going to release the resource. Once it releases the because P1 needs R2 as well, right? So once it releases the resource, it's going to use the resource because this is going to release the resource. But let's P1 see P2 can if holds the P2 holds the resource R2, but doesn't have problem with R3 because R3 is higher order resource than R2. If P2 requests for the R3, it can there is no problem. It can do. Only problem happens when it requests a resource which is of lower order. Is that clear? So if it cannot request resource which is of the lower order. Order means the number. Is this point clear? Are you able to find it? See, pre-process has to acquire resource only in the increasing order. If it is not possible to acquire resource in the increasing order, then the process will voluntarily relinquishes all the resources that is held. It's not just that resource, it's going to leave all the resources so that other process can complete and do it. Okay, so this is the circular wait condition. So through the circular wait, relaxing the circular wait condition by ordering the resources, we can prevent the deadlock from happening. Is that clear? Any questions? Nadisa and Stephen and Eamon and I don't know who else is joining from the Zoom. Are the things clear? What I'm trying to explain?
Yeah, for me, yeah.
Okay, how about others? Stephen?
Yes.
Okay, Elijah, Jad, Sean? Okay. All good. Okay, very good. Okay, so this is the deadlock prevention strategy. And another strategy I was telling is that in deadlock detection, see, and recovery. So this is very simple method detection. Of course, deadlock has happened. We can find the deadlock happen through the graph actually. So that through the graph, we know that the deadlock has happened. This is a very simple algorithm. What is the simple algorithm? See, I think I have written the notes here. I don't know where I wrote the notes. I think this is deadlock. Okay. See, if all these process P1, P2, P3, so let's say circular wait condition circular wait has happened. Okay, and everything is waiting for each other. You draw the director graph, you'll see that there is a deadlock. What this is telling is that kill the process, kill one process. Okay. So if you can kill the process and see whether the deadlock can be avoided or not. If killing one process, I said that, in the previous notes, I told that how many minimum number of is required, a resource required, how many processes are there, right? So if there are 5 resources, then you allocate one resource separately and there are 4 processes and each process requires 2 resources. Then each one will take hold of 1 resource and the 5th resource, whoever gets a turn, it will use and it will release like that, right? Same thing. If you kill the process, if deadlock has happened, let's say it's all circular wait, then what you do is that kill that process. Kill that process means what do you mean by killing that process means? What do you mean by killing the process?
Resources that have been allocated to run the process and be allocated.
Actually, you are removing the process from the RAM. That's it. Killing the process means you are not you are removing from the RAM, out of the RAM. You are removing the process control block, everything you're removing it. Okay, we're killing that process. If that killing the process, you again see whether the deadlock has happened or not. Again, whether it resolves the deadlock or not. If it resolves the deadlock, well and good. If still leads a deadlock, kill another process and see whether the deadlock is there or not. Right? You keep on killing the process. Even though there is a deadlock, then keep killing the process, then they will be left with one process, then one process will succeed and then it will run. Is this clear? This is very simple. You keep killing the process, whichever is leading to deadlock. Tell me which algorithm is used in this operating system right now. I told you several different algorithms. Okay, what are the ways you can, what are the things you can do? What are the different, this thing? One, I said deadlock prevention. You know what is prevention? That is, you acquire the resource in the higher order using, you are relaxing the condition for circular wait, right? So deadlock handling mechanism, I gave you 3 strategies. See, handling, its spelling is HADN, deadlock handling mechanism. I gave you strategies. First strategy is deadlock prevention. What is deadlock prevention mean is that only we are relaxing the condition. We don't want to violate the mutual exclusion property. It's going to result in or no preemption of the resource or hold and wait. Okay, only circular wait we are relaxing in the way that a process will voluntarily relinquish this resource if it is going to request a resource which is of a lower order, because the resources are numbered from 1 to n. So it can always request a request in the higher order, it will be granted, but it's going to request lower order, that resource will not be granted. It is going to relieve all the resources, and so that other process can do this thing. That was the deadlock prevention. Through circular wait, we are achieving that. Is that clear? This is just right now I just spoke about it. And of course, we saw what is and deadlock prevention is, I was telling, right, one example, I think, I think you can make an analogy. I don't know whether it makes sense or not. See, I think I want to say Ben is going to I was using this example, Josh house or whatever, Joshua house. So see, it is going to rain, then Ben is not going to do anything. He's going to wait until the rain stops and then going to go, right? And another thing Ben can do is that, okay, I don't care. I want to go to Josh house immediately. I need to take some stuff. That means that he's going and taking a risk. Is okay to get wet and get sick, but he is telling that I will take medicine and I will recover. I don't care about the rain. So that comes under the category of deadlock detection and recovery. So we just discovered that we are going to kill the process, basically. I mean, I don't know whether the analogy is making meaningful or not, but another is, what I'm telling is that Ben is having a time machine and is going to predict in the future at what time it is not going to rain. He's going to go, he's at 6 a.m. He's saying that 7 a.m. it's not going to rain. Okay, I'll go at 7 a.m. Or he's telling 7 a.m. again is going to rain very heavily. Then 8 o'clock, okay, there is mild chance of rain. At 8:30, he's telling, oh, there is no rain. Okay, I'll go at 8:30. So that is the deadlock. You're trying to predict the future and you have a time machine. So the time machine, why I'm taking time machine is that because we don't know how many resources needed. So we are assuming in banker's algorithm, we are assuming that these are the maximum number of resources I need. So that is deadlock avoidance. That is the banker's algorithm. Is that clear? So we discussed deadlock prevention, deadlock detection, recovery, and deadlock avoidance, which is nothing but your banker's algorithm. That also we discussed, right? Banker's algorithm is not good for the reason that we need to know in advance how many resources are needed by the process, which is not possible unless until you execute that execute the process. But it is assuming that you know everything in advance. That may be possible if it's a small system, small embedded system. We know that all the process, we can examine the code and how many resources needed, etc. Like control area networks, etc. We know that there are a few number of tasks, then it is possible. But for a system like this, we have several processes running on the computer, and this is called as interactive systems. It is not real-time systems. It is interactive, right? So in real-time systems, a different topic by itself. Anyway, among these 3 techniques, which technique is used by the operating system that you are using for general purpose, or I want to call as general purpose operating system? It's all general purpose operating system. I'm not teaching a course on real-time operating system. I'm talking a course on general purpose operating system, which is your Windows, which is your Linux, or whatever it is, Android phone, or whatever it is. So among these strategies, which strategies is current systems are following? Whether it's following deadlock prevention, deadlock detection, whether it's deadlock avoidance, which one is doing?
Like if it was, rebuild it. I guess like you detecting it and filling it.
Actually, to be honest, none of this is used in real life, general purpose.
They just leave out,
No,
one of the
Jared,
four and
no.
never called their ball.
So only thing is that the fourth strategy, I don't want to tell in advance before, then you will say why I'm teaching this, which is deadlock ignorance. All the general purpose operating system are using the deadlock ignorance. Why? Because all these algorithms, all these things require a code in the operating system, right? Sequence of code. Whether you go for deadlock prevention or whether you go for detection recovery, and whether you go for deadlock avoidance, and deadlock avoidance, I think I told is practically not implementable. Okay, but let's say even if it's implementable, I mean, implementable means in this general purpose operating system, which you are using Windows. See, operating system has to run this code. It has to run this code for every nanosecond. Let's say every nanosecond, it has to see, oh, whether deadlock is there, whether deadlock is there, you know. And if you see, keep on doing deadlock is there, you're running useless code, right? This code is useless, basically. Every one nanosecond, you're going to say, I'm going to run deadlock any of these algorithms, right? Every 1 nanosecond, you're wasting your CPU. And during that 1 nanosecond, you can work some useful process, right? And deadlock is a very, very rare event, right? Very rare event. See, I don't want to give the example. I always take flights. See, we know that flight accidents do happen. Is that right? For that reason, if it's going to happen, then it's going to, of course, people are going to die. There is no chance that, few chances. Last year or before COVID, there was a flight which crashed in Air India flight, landed in Kerala, neighboring state. It was so rainy. Actually, was an expert pilot, but he tried to land the flight, but he couldn't come to complete stop, and the flight split into 2 pieces, and around 18 people died. The rest of the people got, are alive, fortunately. Because of the COVID reason, they were trying to escape COVID and they want to come to, because there was like expatriation flight or something they called, they were trying to move. Even America was doing that. All the people from America came to US, one day everything was crowded, etc. Because they're telling all the flights are shut down, like that. Why I'm telling this thing is that flight, of course, Boeing 737 has some huge problem, I guess, because a lot of this that also recently there was an accident in somewhere in Africa, I guess, South Africa. I don't know, Africa, I guess. I don't know exactly. See, these flight accidents is a rare event. For that reason, we are telling that I never take flight, right? So, of course, if flight accident going to happen, it's going to be very deadly. Of course, I know that. For that reason, we are saying that is 1 in 10,000 or 100,000, or maybe 1 million possibility that the flight is going to crash, right? So the same thing here. I make a same analogy, but I cannot make a same analogy where flight accident, of course, it should not happen. I always take flight. Dying in the flight is not good. Okay. Dying peacefully is good, but dying fear is not good. Okay, anyway, I'm trying to compare. So it's a very rare event. Flight accident is a rare event. Same thing. Deadlock is also a rare event. And why you want to run a deadlock detection algorithm every nanosecond and waste our CPU, instead of that time, you can use that time to do some useful task, right? Is that clear? That's why these algorithms are not used for general purpose operating system. But that is not the case with when you send a rover to the Mars and deadlock can happen. In that case, you are spending millions and millions of money to send to the space, and what is called, they also interstellar space outside the solar system. Also, now these things are going, right? So you don't want to take a chance, and that well-defined task in those systems, that real-time operating system. In that case, you don't want the deadlock to happen, right? In that particular case, maybe you are going to use these kind of algorithms where you want to periodically check whether the deadlock is happening or not. But for general purpose operating system, for Windows and everything, at the end of the day, Samantha is working on an assignment. Suddenly a deadlock happened. She didn't save the assignment for whatever reason. She wrote 1,000 pages and it crashed. I hope it doesn't happen. But if it crashed, and Samantha is at the end of the day, she's going to scold only Windows, and she starts to redo all the assignment, type everything from the beginning.
That's it. If it freezes, right? Freezing can happen at any time. That's why I always ask the students, especially when I'm teaching 100 level courses, ask the student to save, save, save. Control S to save, 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 save. Because you're working in the RAM. Only if we press Control S, if the data is going to be copied, that corresponding page or whatever is going to be copied into the hard disk. Otherwise, it's not going to copy, right? So that's why I always say press Control S, Control S, Control S whenever you're working on a Microsoft Excel or whatever. Because we don't know. It can happen. If it freezes, everything is lost, right? That's the thing. We use deadlock ignorance algorithm. There's no algorithm, we just ignore. Okay. So deadlock ignorance. That's what you can Google about it. None of the operating system, Linux or this thing or Windows is there. You can Google about it, which algorithm uses. I just found it. They don't use any of these algorithms. Is that clear? Any questions? Okay. See, one problem is leading to one problem. That's why we have this topic is huge. One problem. Of course, if I have time, I'll cover real-time scheduling algorithms. Is that clear? Any questions? So definitely there is going to be questions on deadlock, especially on bankers algorithm. Please be sure, William Sterling, if you can understand, it is very well and good. I was reading William Sterling for the first time, trying to read and understand this algorithm. Of course, my research is not on this deadlock. I told you it's in scheduling. Trying to understand deadlock, bankers algorithm from Sterling's book, very, very, very hard to understand. It's not clear at all. It's very difficult, confusing way they've written. Same thing with a lot of books on mutual exclusion and synchronization. Their explanation is at all not satisfactory. They try to explain verbally. It is not verbally means the text by in the terms of not verbally, sorry, in the form of text. It is difficult to understand what the others are trying to say. It's very difficult concept. Sometimes it's difficult for the authors to write textbook. Even to write a paper text, this thing, it's very difficult. So with this, I want to complete the topic on deadlock. And finally, I just want to have one announcement. Please do show your work on CPU. If you're doing the project component, please update me where you are. And I need 4 algorithms to compare. And of course, this I didn't show you. And this I showed you to Will when he was in my office. See, I just uploaded this paper. Actually, this paper I didn't publish because for the reason that I know the paper is not well written. I'm not interested in publishing papers. If it's not well written or if there's some clarity or no clarity is missing or whatever. I think if you go to semester project, you will see that this is my, of course I wrote the I wrote the paper while I was doing masters, but I didn't do any kind of, I didn't publish this. So if you want, this is a round robin, a modification of round robin. I'm trying to say the whole paper. I'm trying to say what is the problem with the round robin. Okay. Related works, etc. And what I want to say is that this is my pseudocode for round robin. If you don't know how to implement the round robin algorithm, please refer to this paper. Don't use the modified round robin. This is a modified round robin pseudocode. You don't have to compute the credit and all. So I just say credit. I think I use the term credit. So the CA is credit. So how much time it didn't use, because I'm classifying jobs into IO bound and CPU bound jobs. So similar way, just do the round robin algorithm. If you don't know how you can implement the round robin, I gave the pseudocode. So do this and understand this. If you don't understand, please come to me, office hours. For the, I think for this project, I don't need to write like whole paper. I want you to write the discrete event simulator and compare whatever you want to compare and try to get some information from the algorithm. Like a data science, like a lot of data is there and you want to interrupt from this data. That's called information visualization or whatever information. So interrupting process data is nothing but information, right? So much data is there in the internet and you want to get some meaningful information. That's like same thing like that. It's not like one-to-one analogy, but I'm trying to make an analogy here. I'm trying to say that whatever response time or whatever, see, one thing I don't like, this is my supervisor made a mistake, like all this kind of notations, etc. I don't like, that's why I don't like, if I want to publish I have defined what is the turnaround time, what is the, see, response time for me is different from, I define according to the many textbook, response time is the one at the first time at which it grabs the CPU, a process grabs the CPU, that is called as the response time. But I am redefining the response time as the average of times between the consecutive usage of the CPU. So again, when it gets the CPU, so that is my response time. So I just recalculate. I don't like that. See, first time it gets the CPU, and we cannot say the response time is good. I want to say the response time is good. For consecutive times also, it has to get the CPU faster, right? So that's why change the response time definition in this paper. So trying to compare the graph, and here I used IO bound job and a CPU bound job, how my algorithm prefers, see, the problem with round robin algorithm is that it prefers always CPU bound job. The response time for the CPU bound job is lesser than response time for the IO bound job, because IO bound job always spends a lot of time in IO and it has to join at the end of the queue. So for that reason, I made a simple modification is that how much time it spends the IO, I'm just calculating that, I'm adjusting the time quanta. Next time I'm giving the chance more quanta for the IO bound jobs to complete the execution. I'm trying to give its chance. How much time I lost, that amount of time I'm giving back to that IO bound job. That was actually the idea of this paper. So I'm dynamically adjusting the quanta, because what is it? Yeah, but it's cool, but I didn't publish. Anyway, I don't know if others published. This was back in 2004. I'm talking, okay, 2004 or 5, right? So if I want to publish, I want to. And other thing is the Sure Grant. I just posted that information D2L. So you can do anything on Sure Grant. There's no enough application they receive, so they extend the deadline. Please do apply for Sure Grant. That is going to be good for your resume. Whether you work with me or work with any other professor, it doesn't matter. Please do apply for Sure Grant. That will be good for your profile. That will be good for getting a job or maybe master's degree or whatever. So please do apply for the Sure Grant. Okay, that's my conclusion. I think I don't want to overrun time. All right. And thank you for having a nice class. Okay, Ben, I'll answer your question. I'll stop this and I'll answer the question. And Zoom students, do you have any questions?
No, I think I don't. Why I didn't publish it?
The reason is that I didn't like the way the paper is written. I didn't have time. I changed my topic to plant modeling, biological modeling. So I was working. I was working on a more serious problem than this to understand how emergent patterns come. So I was understanding biology, and PhD was different topic. That's the reason. Yeah. Maybe if I have chance, I'll publish with you. Okay, Nadia. We can do related work and do a little bit more survey and see what others have done in the last 20 years and how it's different. If we can make a difference, then we can publish this. Okay. All right.
Thank you, Jay.
Yeah.
Exciting. Thank you so much. Thank you, Jay.
Thank you. May 1st, I told May 2nd. May 2nd is on Monday. May 2nd is the final exam. I will tell you in the next class. Okay. On my next week. Okay. Thank you guys and have a nice evening. Bye-bye.
You too. Bye-bye.
Yeah.